Let's talk about the cerebellum, the anatomy, the gross anatomy of the cerebellum. Okay, so our objectives for this is to be able to describe the gross features and subdivisions of the cerebellum, differentiate between the longitudinal divisions of the cerebellum and the anterior posterior divisions of the cerebellum, and ascribe a general function to each. Describe the posterior peduncle, describe the structure actually of the cerebellar peduncles, and then list the layers of the cerebellar cortex and the cells contained within it, as well as the connections that we have. Then list the fiber types of the cerebellum and the cell systems associated with each. Describe the major cerebellar pathways, right? Describe the results of cerebellar dysfunction, and also describe the results of cerebellar lesions. So basically an overview concerning the cerebellum. The cerebellum during development developed from the ulnar plates, right, of the metencephalon. And it's located infratemporally, actually above it is the tentorium cerebelli, right, the fold of dura mater within the posterior cranial fossa, and lies between the temporal and occipital lobes and the brainstem. It has three primary functions: the maintenance of posture and balance, one, the maintenance of muscle tone, and the coordination of voluntary motor activity. So it's also a component, right, of the motor system. Its weight is averagely 150 grams in an adult. This is about 10% of the weight of the cerebral hemispheres. It consists of a midline vermis and two lateral hemispheres. When you look at the cerebral hemispheres, we have got two hemispheres joined in the midline by the corpus callosum. But if you're looking at the cerebellum, we have the vermis at the midline. It's covered by a three-layered cortex, which is actually uniform, formed into folia, right, and fissures. Then we have the white matter and the intra, right, nuclei that we actually find within the white matter, which is the deep cerebellar nuclei. So here in this picture, we appreciate the cross-section, right? And I shall indicate what we are seeing here. So here is the cerebral aqueduct. Here is the midbrain. Here are the pons. Here is the medulla. And at this point, we appreciate a ventricle, which is the fourth ventricle. So you can see we actually find the cerebellum being found forming the roof of the fourth ventricle, right? And we actually see that forming, right, the upper part of the roof is a part of the cerebellum that we call the superior medullary velum. Here with the superior medullary velum. And then here, forming the lower part of the roof, actually, is the choroid plexus. Okay, so that's very important for you to note that the choroid plexus is found in the lower roof of the fourth ventricle. Then we also see that here we have, so here is the midline. So it was actually cut at the midline. We're actually appreciating the structure of the vermis. This is one hemisphere at that point. Here is the vermis, and this is actually the tonsil. And this structure can actually herniate through the foramen magnum if there is increased intracranial pressure. That is tonsillar herniation. So here we actually appreciate the depressions. So we actually appreciate the fissures, right? And then we actually see that we have these depressions and these folds, and these folds are what we call the arbor cerebelli that we actually see there, which appear like a tree, right? Now, the external features of the cerebellum, we have the superior and inferior surfaces of the cerebellum. On the superior aspect of the cerebellum, we actually see that we have the vermis that actually blends into the hemispheres. And remember, we said the vermis divides the cerebellum into two hemispheres. Then we actually see on the inferior surfaces, the two hemispheres are separated by a deep depression that we call the vallecula. So we're saying on the superior surface, the vermis is almost at the same level with the hemispheres. But on the inferior surfaces, actually there's a depression at the point where we see the vermis. That is called the vallecula cerebelli. The fissures of the cerebellum, we have actually these three large fissures. We have the primary fissure, or the fissure prima, and then we have the horizontal fissure, and then we have the posterolateral fissure. And the posterolateral fissure is the first one to appear during embryonic development. Now we need to appreciate that anterior to the primary fissure, right? So if I'm to do a little drawing and I say this is the primary fissure, right? This is the horizontal fissure, and this is the posterolateral fissure, right? As we'll be seeing here, right? So this will be the anterior lobe. Sorry for that. This will be the anterior lobe of the cerebellum, right? Let me stop my shape a little bit. So this will be the primary fissure, the horizontal fissure, and then the posterolateral fissure. We appreciate that anterior to the primary fissure, what we see here is the anterior lobe, right? And anterior to this posterolateral fissure, here at the lower part, inferiorly, is the lobe that we call the flocculonodular lobe. Between the primary fissure and this posterolateral fissure, we actually see the posterior lobe. So the cerebellum is divided into two hemispheres and then divided into three lobes by means of this fissure and this fissure. So what's the use of this fissure? The horizontal fissure is used to just demarcate the surfaces of the cerebellum. Everything above the horizontal fissure is on the superior surface. Everything below this is on the inferior surface. So that is a view of the cerebellum superiorly. So we actually see this, the superior vermis, that is blending with the hemispheres. And then we appreciate that here we have the midbrain. Here is a fissure, which is the primary fissure. And I said anterior to the primary fissure, everything we see at this point is the anterior lobe. Everything we appreciate at this part is the anterior lobe. And at this point, we start to see a depression that we call the vallecula cerebelli, where we see the inferior vermis. So here in this diagram, we're appreciating the position of the cerebellum. We said superior to the cerebellum is the tentorium cerebelli. Then we also have got a fold of gyramater that goes in this depression, the valleculae, right? Which is called the falx cerebelli. All right, so that is the inferior view. At this point, we appreciate the medulla. And here we see that we have these valleculae. And then through that, we can actually then see the inferior vermis. And here is the horizontal fissure. And I said anything superior to the horizontal fissure is just a superior surface. Anything inferior is basically an inferior surface of the cerebellum. The horizontal fissure does not divide the cerebellum into lobes, but actually divides into surfaces. Now we are appreciating the communication of the cerebellum with other parts of the brain. We actually see that the cerebellum is then joined to the brainstem by use of these peduncles. So we actually have got these peduncles, 3 on each side. We appreciate that medially we have the superior cerebellar peduncle. Intermediate is the inferior cerebellar peduncle. And laterally we have the middle cerebellar peduncle. So that is MIS from Latin. So that's MIS, MIS from lateral, so superior and then inferior, and then we have the middle. Then we have structures that we actually see from the anterior view of the cerebellum. So here is the posterior lobe, which is the flocculonodular lobe, right? So what we actually see is that we have a structure here, which is part of the vermis, that is called the nodule. Then part of the hemisphere, that is called the flocculus. So joining the flocculus and the nodule, they form a lobe that is called the flocculonodular lobe. Are we together? Yes. Then the cerebellar lobes. We have got phylogenetic divisions as well as functional divisions. They also go along. We have the anterior lobe of the cerebellum that can also be called the spinal cerebellum, works with the spinal cord. Like we said, it's anterior to the primary fissure, and then it receives input from stretch receptors, or basically proprioceptive receptors, the Golgi organ tendon, the muscle spindles, right, and the joint capsules via the spinal cerebellar tracts. And we understand, like we talked in the spinal cord, right, the dorsal spinal cerebellar tracts. Then also the cuneo-cerebellar tracts as well. So it plays a role in the regulation of muscle tone. So this is one thing you must take note. It plays a role in the regulation of muscle tone. So remember, one of the principal functions of the cerebellum. Then functionally, so this was basically anatomical divisions. Functionally, it is related to the vermal region and the paravermal region. So functionally, it's related to the vermal region and the paravermal regions. We'll explain these regions. Posterior lobe, this is what we call the neocerebellum. Or in other words, we can call it the corticocerebellum. Or we can call it the pontocerebellum. Or the cerebrocerebellum. So it lies between the primary fissure and the posterolateral fissure, like we said. And it actually receives input from the neocortex, right? The cerebral cortex, right? Via the cortical pontocerebellar fibers. So we actually see that from the cortex, we have fibers that run to the pontine nuclei. So those are the cortical pontine fibers. From this pontine nuclei, we have decussation to the opposite side, and then they run to the cerebellum through the middle cerebellar peduncle. It plays a role in the coordination, one of the principal functions as well of the cerebellum. Coordination of voluntary motor activity. So it will be working with the cerebral cortex and also working with the basal ganglia. Functionally, it is related to the lateral hemispheres. Here now is the flocculonodular lobe that we also can call the vestibulocerebellum. So it works with the vestibular system. The vestibulocerebellum. This can also be called the archicerebellum. This is the oldest part of the cerebellum by phylogeny. So we see this system or this part of the cerebellum within the aquatic animals. So we actually see it within the aquatic animals, so within fish. So actually see it within the aquatic animals, this part of the cerebellum. And this one is then appreciated in higher animals, actually, right? Like humans. So we actually see it within mammals. So that's the posterior lobe, or the neocerebellum. It's the new form of the cerebellum. This is the old form that can also call the archicerebellum. So what is the function? It consists of the nodulus, of the vermis, and the flocculus part of the hemisphere. Hence, it's called the flocculonodular lobe, like I've shown you in the previous slide. It receives input from the vestibular system. So it receives input from the vestibular nuclei, as well from the vestibular apparatus of the internal ear. Plays a role in the maintenance of posture and balance as well. So from here, we have the spinal cerebellum. When it comes to phylogeny, this is intermediate. So this is actually intermediate. So this is what called the paleocerebellum. So we have the paleocerebellum. So it's called the paleocerebellum. So firstly, we start with the anchicerebellum, which is the oldest, which is the vestibulocerebellum within the aquatic animals. As the animals now move to the land and they start to walk, right? Now we need the use of the spinal cerebellum. That's why it now regulates the muscle tone. So we actually see them within the reptiles. When we say the neocerebellum is only seen in higher animals, whereby now there's now coordination of voluntary movements. Okay, that's very important for you to know. Then we have the longitudinal organization of the cerebellum into zones. Now, this is basically a functional division of the cerebellum. And these zones basically are associated with specific cerebellar nucleus and pathways. So the zones that we have the median zone, right? The intermediate zone and the lateral zone. So we can also call them the vermal zones around the vermis. And then we have the paravermal zone, and then we have the lateral zone. So we'll talk of the deep nuclei within the cerebellum. But for now, appreciate that the vermal zone projects to the fastigial nucleus. Projects to the fastigial nucleus. The paravermal zone projects to the emboliform and the globus nucleus. The lateral zone projects to the dentate nucleus. With the three parts of the cerebellum that we've talked about in the previous slides, we actually see that this zone works with the vestibulocerebellum. Hence, the vestibulocerebellum works with the fastigial nucleus. This paravermal zone works with the spinal cerebellum. Hence, works with these two nuclei, the emboliform and the globus. Here, this one actually works with the corticocerebellum, or the cerebrocerebellum, or the pontocerebellum, or the neocerebellum, the dentate nucleus. So these are basically zones, how we divide the cerebellum. So there's a median zone where we see the vermis, and the paravermal zone and a lateral zone. At this point, we then appreciate that we have the vermis at the midline. And here we can appreciate the parts of the hemispheres. So from inferior, going posterior, and until we reach anterior, these are the parts of the hemisphere. So remember, we have a nodule, and here we have the flocculus. And this forms the posterior lobe. So parts of the lateral hemispheres with the flocculus. Then we have a tonsil. From there, we have what we call the biventral lobule. From there, we have what we call the grassa lobule. Then we have the inferior semilunar lobule and the superior semilunar lobule, the posterior quadrangular lobule, and the anterior quadrangular lobule. So we have anterior quadrangular lobule, the posterior quadrangular lobule, the superior semilunar lobule, and then here we have the horizontal fissure. We are done with the superior surface. For the inferior surface, we have the inferior semilunar lobule, the grassa lobule, the biventral lobule, and the tonsil. But what I want you to understand is we have a tonsil inferiorly. For this is now seen when it comes to tonsillar herniation. And these are the parts actually of the vermis. Here we actually see the nodule. Here we actually appreciate what we call the uvula. Also see from the anterior view. And at this point, we appreciate what we call the pyramid. And this one is what we call the tuba, the folium, right? We have what we call the declive, and the cumen, and the central lobule, and the lingula. So you actually see in textbook, they talk about this one, and they talk about these ones, right? Because they appear on the anterior surface and are also related to the fourth ventricle. So these are basically the divisions of the cerebellum. Then in terms of lobes and functions, remember I said we have the order form, the archicerebellum, the spinal, the vestibular cerebellum, right? Then we have the intermediate, the paliocerebellum, right? Also called the spinal cerebellum. And then we have this newer form, right? Which is the pontocerebellum or the cortical cerebellum, right? Or the cerebral cerebellar system. Appreciating from this diagram, we see that the flocculonodular lobe is the oldest and is the archicerebellum. That's why I say the first feature to appear is the posterolateral feature, even in development. The spinocerebellar system or the paliocerebellar system works with the anterior lobe. The anterior lobe, we see it being anterior to the primary feature. So the anterior lobe is everything anterior to the primary feature. And at the same time, it takes a little part functionally from this part of the vermis. So we actually say that the pyramid and the uvula are part of the anterior lobe. That's why you see here, they have the same color. And then we need to appreciate that the rest now of the posterior lobe, right, except the pyramid and the uvula, is part of the neocerebellum that deals with coordination of movements. These ones, they'll deal with muscle tone. These ones, they deal with equilibration. Here we are, phylogenetic divisions. We have the archicerebellum, the oldest, paliocerebellum, the intermediate, neocerebellum, the new one. The anatomical components, we see that this is the flocculonodular lobe and the lingula. Here is the lingula at this point. So we see it's the same color, right? And the connections, is chief connections with the vestibular apparatus. That's the vestibular nuclei, as well as the vestibular apparatus within intermediate. Then functions is basically maintenance of the body equilibrium. And then we actually see that we have the functional classification. This is the vestibulocerebellum. Here we see the paliocerebellum. It is anatomically, right, seen on the whole of the anterior lobe, except the lingula. The lingula is seen here on the archicerebellum. Then we take the pyramid and the uvula of the posterior lobe. Chief connections are with the spinal cord in regulation of muscle tone. Functions, maintenance of muscle tone, and final control of movements. Right. Here, that is the spinal cerebellum. Here we see the neocerebellum, which is the new part, the new form of the cerebellum, seen in higher animals. The whole of the posterior lobe, except the pyramid and the uvula, because these are now parts of here, the anterior lobe, functionally. Main connections are with the pons. And via the pons there, right, you actually see that the connections are actually coming from the cerebral cortex. And it's actually responsible for fine coordination of voluntary movements. That is what we call the cerebellum. So this is very important for you to understand and appreciate when it comes to the anatomy, right, and the functions of the cerebellum. Let's talk about these peduncles, how the cerebellum is actually anchored to the brainstem. The peduncles are actually three in number, as we have appreciated from the previous slides. We have the superior cerebellar peduncle, the mid-cerebellar peduncle, and the inferior cerebellar peduncle. I will start with the inferior cerebellar peduncle. The inferior cerebellar peduncle is mostly fibers coming into the cerebellum. We also have got fibers leaving the cerebellum, right? So it has got both afferent and efferent fibers. So the inferior cerebellar peduncle connects the cerebellum to the rostral medulla and the caudal pons. And it consists of two bodies or two divisions. We have number one, what we call the restiform body, and number two is what we call the juxta-restiform body. The restiform body contains afferent fiber system. It's basically the afferent fiber system. That is the dorsal spinocerebellar tract, the cuneo-cerebellar tract. This is basically coming with proprioception, right? This is basically coming from the accessory cuneate nucleus, the cuneo-cerebellar tract, and the olivo-cerebellar tract. That forms the restiform body. The restiform body is basically afferent and efferent, being the vestibulocerebellar fibers and the cerebello-vestibular fibers. So just remember, the juxta-restiform body is to do with the vestibular system. Fibers coming from the vestibular nuclei to the cerebellum and coming from the cerebellum to the vestibular nuclei, that forms the juxta-restiform body. Otherwise, the rest is the restiform body. That is the inferior cerebellar peduncle. And it's also related laterally, or it's actually what forms the lateral borders of the fourth ventricle, actually. So it forms the lower lateral walls of the ventricle. Then we go on to the middle cerebellar peduncle, which is the largest of them all. Now, this connects the cerebellum to the pons and contains only fibers entering the cerebellum, which is afferent fiber systems, right? From the pontine, the contralateral pontine nuclei, right? And this is now working with the neocerebellum. So these fibers are actually come from the cerebral cortex as the corticopontine fibers, right? And then from there, cross the midline and then goes to the opposite cerebellum hemisphere. Then here we see the superior cerebellar peduncle. Now, this is both afferent and efferent fibers. So it connects the cerebellum to the rostral pons and the caudal midbrain. The rostral pons, the upper part of the pons, and the lower parts of the midbrain. So the major output pathways from the cerebellum. So remember I said the inferior peduncle is mainly input. Middle peduncle is only input. Superior peduncle is mainly output. So the fibers leaving the cerebellum, the efferent pathways. We have fibers coming from the dentate nucleus, right, to the red nucleus, to the thalamus. These are what called the dental rubro-thalamic tracts. So these dental rubro-thalamic tracts actually coming from the dentate nucleus to the red nucleus, to the thalamus. Then from there, they radiate to the cortex. So they can also be called the dentato-rubro-thalamo-cortical fibers. Then we have what we call the interposital rubro-thalamic tracts. This is basically coming from the nucleus interpositus. We'll talk about the nucleus interpositus. And then we have the fastigiothalamic tracts coming from the fastigial nucleus to the thalamus. And at this point, we see the afferent pathways. These are the fibers entering the cerebellum. Where are they coming from? We actually see the anterior spinocerebellar tract. This is very important for you to understand that. The ventral or the anterior spinocerebellar tracts, they use the superior cerebellar peduncle. And then the dorsal spinocerebellar tracts, they use the inferior cerebellar peduncle. We also see the fibers coming from the trigeminal nuclei, the mesenteric part of the trigeminal nuclei. These are what called the trigeminal cerebellar fibers. Then we actually see what we call the cerebellar fibers. These are actually coming basically from the reticular formation. Right. Then let's look at the histology of the cerebellar cortex. The cerebellar cortex has got 3 layers, and the layers are uniform all over compared to the neocortex. So the cerebral cortex actually has got 6 layers that are not uniform all around. That's why we have got the agranular cortex and the granular cortex. But for this part, we have got uniform layers all around, and also a uniform structure. So at this point, we actually see 3 layers, which are the molecular layer, the Purkinje cell layer, and the granular layer. We'll start with the molecular layer. So this is the outer layer, right? The outer layer, which is actually cell space, right? And it is actually below the pyometer. So basically, this is a region whereby we have many synapses and dendrites as well as axons. So it contains dendritic arborizations of these Purkinje cells. Now, these Purkinje cells are large cells of Golgi type 1, right? So their dendrites are found in the molecular layer. And the parallel fibers of the granule cells, as well as other cells, the stellate, as well as the basket. So let's appreciate that we have another layer underneath the molecular layer that we call the Purkinje cell layer. So this is a thin layer actually. So it's found between the molecular and the granular layer, and it contains the cell bodies, these flask-shaped cells, the cell bodies of the Purkinje cells. Then we go on to the deepest of them all, the granule cell layer. It's found between the Purkinje cell layer and the cerebellar white matter. Contains the granule cells, the Golgi cells, and the cerebellar glomeruli. We'll talk about that. The cerebellar glomeruli is basically a mass, right, found within the granule cell layer, composed of the presynaptic terminals of the mossy fibers that we call a rosette. So if I have this one here is a rosette, right? That's a terminal knob of the ascending fiber, or of these fibers that we call the mossy fibers. A mossy fiber is a type of the afferent fibers coming into the cerebellum. I will talk about these fibers later on. So with that, we also then see that in association with this, right, is a cell, right, which is the granule cell. So around this rosette, we actually see the granule cells. The granule cell has got an axon that then bifurcates within the molecular layer and form what we call the parallel fibers. So this one bifurcates, forms the parallel fibers, forming the parallel fibers. And the granule cell is actually excited to other neurons that we actually see within the cortex. So we actually say the granule cell is the only cell within the cortex that has got excitatory effects. Then we have other cells that we call the Golgi cells, or the Golgi neuron. The Golgi neuron is basically inhibitory. So the Golgi neuron is then basically inhibitory to the granule cell. So this structure that we then see at this point is what we call the glomeruli. Formed by the Golgi neuron, this granule cell, and the rosette, or the terminal knob of the mossy fiber. This is what we appreciate within the granular layer. So the neurons actually that we see within the cerebellum, we have what we call Purkinje cell, the largest. So this basically conveys the only output from the cerebellar cortex. So from the cortex, the only output is through the Purkinje cells. And it's actually inhibitory. They produce GABA. And this GABA is being released to the deep cerebellar nuclei. as well as the vestibular nuclei. So we say the output of the cerebellar cortex is only to the deep cerebellar nuclei, nothing else, with an exception of the vestibular nuclei. That's why we say the vestibular nuclei during development migrated actually from the cerebellum. So we say the vestibular nuclei is actually the nuclei of the cerebellum that migrated. That's why it has direct communication with the cortex. The Purkinje cell is excited by parallel fibers, right? So remember the parallel fibers, these are basically the axons, right, of the granule cells, and also by what we call the climbing fibers, right? So when it comes to input to the cerebellum, every input or the input to the cerebellum is either through the climbing fibers that we call the climbing fibers, right? Or the mossy fibers that we actually see these ones, the climbing fiber or the mossy fiber. Now I want you to understand the difference between a climbing fiber and a mossy fiber. The climbing fibers generally are non-divergent. That means they are discrete and precise of where they're going. And the climbing fibers are fibers that are coming from the olivary nuclei only. So the olivocerebellar fibers are these climbing fibers. The mossy fibers are all the fibers coming into the cerebellum from wherever they're coming from. They're called mossy fibers. But I remember the climbing fibers are basically coming from the olivary, the inferior olivary nucleus. So they excite, so they climb around the dendrites of these Purkinje cells. So we call them the Purkinje fibers. So the Purkinje cells are inhibited by the basket and the stellate cells. The basket and the stellate cells. Let's go to the granule cell. The granule cell is excited, which I said this is the only neuron within the cortex, the cerebellar cortex, that is actually excited. So it actually excites the Purkinje cell, like we're seeing here, through its parallel fibers. So it excites the Purkinje, the basket, the stellate, the Golgi cells. So all of these cells are excited by these granule cells through their parallel fibers that run within the molecular layer. And the granule cells in turn are inhibited by the Golgi cells. So the granule in turn are inhibited by the Golgi cells. And they are excited by the mossy fibers, like I've shown here. They're excited by the mossy fiber and then inhibited by this Golgi neuron. So there we find that within the molecular layer, we see the stellate cells inhibitory, basket cells inhibitory, right? In the Purkinje cell layer, we find the Purkinje cells inhibitory, but these ones are inhibitory to the nuclei within the cerebellum, the deep cerebellar nuclei, as well as the vestibular nuclei. The granule cells are the only ones that are actually excitatory, producing glutamine. Within also the granular layer, we see the Golgi cells that are inhibitory. And these ones are inhibitory to the granule cells. The Purkinje cells, I said they're inhibitory to wherever they're going from the output, which is the deep cerebellar nuclei and the vestibular nuclei. The basket are inhibitory to the Purkinje cells. The stellate are inhibitory to the Purkinje cells. This is the neural circuitry that we actually find within the cerebral cortex. So looking at this, we have the Purkinje cell. And here is the arborization of its dendrites. And we see that here we have a climbing fiber, climbing around it, exciting it. Then we see here is a mossy fiber. And remember, I said the climbing fibers are only coming from the olivary nucleus. Here we see the mossy fibers of all the afferents coming from everywhere. The mossy fiber coming to the glomeruli that you actually see within the granular layer. At this point, we appreciate these basket cells that are inhibitory to these Purkinje cells. We also appreciate that within the most superficial part of the molecular layer are the stellate cells. They are also inhibitory to the Purkinje cells. Then within the granular layer is this glomeruli, formed by the rosette, the terminal knob of the mossy fiber, right? And these dendrites of the granule cells, right? That is actually excitatory. And then we see these axons going up and then forming these parallel fibers that are actually excitatory whenever they're in contact with the Purkinje dendrites. Then we see the Golgi neuron that is basically inhibitory to these granule cells, right? And then we see the output from the Purkinje cells, which I said it's always inhibitory. Fibers to the cerebellum. The mossy fibers are basically excitatory fibers that are basically coming from all regions except the olivar nuclei. So they terminate as mossy fibers on the granule cells that we say they terminate as a structure that we call the rosette. And they basically excite the granule cells, right? And the granule cells will then also put out their excitation to the parallel fibers in the molecular layer. Here we actually then appreciate also the climbing fibers. These are apparent excitatory fibers only coming from the olivar nucleus. And then they terminate on neurons of the cerebellar nuclei and also on dendrites of the Purkinje cells. One thing you need to understand with these afferent fibers is that if you have an afferent fiber going to the cortex, doing whatever it will do to the cortex there, right, depending on the mode of action there, all of these mossy and climbing fibers are basically excitatory when they get to the cortex. So they're basically excitatory when they get to the cortex. But they also send collaterals that are also excitatory on the deep cerebellar nuclei, that are also excitatory on the deep cerebellar nuclei, right? And then what we need to appreciate is that whatever will happen in the cortex, the only output we say is through the Purkinje cell. And the Purkinje cell, we said it's only inhibitory to the deep cerebellar nuclei and the vestibular nuclei. So at this point, we see inhibition. And here we see the Purkinje cell being activated. So what we're actually seeing here is that if you've got input coming at this point, I'm input coming at this point, right? Action potential is firing at this point. We have activation of this nuclei, the deep cerebellar nuclei, and then you have inhibition. And through this fiber here, it will actually activate an inhibitor. And then here, we then have inhibition. So that is what we call neural sharpening or neural sculpturing. That you have basically excitation and basically inhibition at the same time if you've got much input coming here, right? That is what we call neural sharpening. The deep cerebellar nuclei, basically, we have got 4 pairs of the deep cerebellar nuclei embedded within the white matter of the cerebellum. In a lateral direction to the medial, we have the dentate nucleus that looks like teeth, so it's called dentate. And then we have emboliferous nucleus or the emboliform nucleus. Then we have this globe-like nucleus that we call the globose nuclei. And then we have the fastigial nucleus. So we have the D from lateral, the E, the G, and the F, right? I don't know what mnemonic you can create from there, right? And these 2 nuclei at the middle, these ones, are called the nucleus interpositors because they are interposed between the dentate and the fastigial nuclei, right? The fastigial nuclei can also be called the roof nuclei, right? It's found within the roof, actually, of the fourth ventricle. So that's why it's called the fastigial nuclei. The fastigium, right? That is actually a Latin word actually for a roof. Here we say the embolic form and the globus are called the interposed nucleus. The input to the cerebellar nuclei is from, right? The source is outside the cerebellum, that is the moss and the climate fibers, which is excitatory. And then the Purkinje cells of the cortex, which is basically inhibitory, right? Extrinsic input, right, is basically from the pontine nuclei, the spinal cord, olivular nuclei, right, and also what we call the precerebellar reticular formation. Most of these afferents are collateral branches of fibers proceeding to the cerebellar cortex, like we have shown here. Most of these fibers are basically collateral, right? A few rubrocerebellar, so coming from the red nucleus to the cerebellum, fibers end in the interposed nucleus, right? The fastigial nucleus receives afferents from the vestibular nuclei and also the vestibular nerve. So remember, I said the fastigial works with the vestibulocerebellum in terms of balance. So we actually say that the vestibular nuclei, right, and the vestibular nerve. So remember the vestibular nerve, right, cranial nerve number 8, right, can synapse. It actually synapses with the vestibular nuclei, and then from the vestibular nuclei, fibers going to the cerebellum. Or the vestibular nerve can bypass the vestibular nuclei and go straight to the cerebellum. Right. So the fastigial nucleus projects to the brainstem via the inferior cerebellar peduncle. Right. Remember how the cerebellum can also then feed back to the vestibular nuclei. Efferents from other nuclei leave the cerebellum through the superior cerebellar peduncles and end in the brainstem and thalamus. So all the other nuclei now, that's now through the superior cerebellar peduncle. Input to the cerebellar, to the central nuclei from outside the cerebellum is excitatory, right? The input from Purkinje cells is actually inhibitory through the release of GABA. Then the cerebellar pathways. If the vestibulocerebellar pathway, right? So remember the vestibulocerebellar pathway, right? This is now in maintenance of posture and balance, and also helps in coordination of eye movements. So we also see that we have got fibers that are basically coming as well from the semicircular ducts and the otolith organs. And then they project to the oldest form of the lobes, which is the flocculonodular lobe. Right, so there we see the flocculonodular lobe, so receives also visual input from the superior colliculus, right, and also the striate cortex, right? So this is basically from the visual, for the visual system, right? And the flocculonodular lobe, in turn, then now projects the vestibular nuclei. The vestibular nuclei projects via the medial longitudinal fasciculus to the what we call the oculogyric motor nuclei, or the oculogyric centers. So these are basically the nuclei that basically move the muscles of the eye. So it has come from the visual system, right? It has gone to the flocculonodular lobe, from the flocculonodular lobe back to the vestibular nuclei. From the vestibular nuclei, now we project through the medial longitudinal fasciculus. This is like a highway within the brainstem to basically these oculogyric nuclei for movement of the eyes, right? So the vestibular nuclei also then project via the medial and lateral vestibulospinal tracts to the spinal cord to regulate basically the movement of the neck muscles as well as the anti-gravity muscles. So understand that the lateral vestibulospinal tract supplies the anti-gravity muscles, which is the extensors. The medial, right, we can also be called the medial longitudinal fasciculi or the medial vestibulospinal tract, also then supply muscles of the neck, right? Then we have the spinal cerebellar pathways. So this one actually then maintains posture and muscle tone, right? And then it has to do with the truncal muscles as well as the proximal muscles of the limbs. So here we're dealing with the vermis, right? Here we're dealing with the vermis, the vermal region. So it receives the spinocerebellar and the labyrinthine input. And then it also then projects to the fastigial nucleus, right? And then from there, we see that it has excitatory output from this fastigial nucleus, right? And then projects via the vestibular nuclei to the spinal cord, right? And also then projects to this motor nucleus of the thalamus, which is the ventrolateral nucleus of the thalamus. The ventrolateral nucleus of the thalamus receives input from this fastigial nuclei, right? And then projects to the precentral gyrus, right? Then the precentral gyrus now gives rise to the anterior corticospinal tract, which now regulates muscle tone of the truncal and the proximal muscles. Remember, the anterior corticospinal tract consists of fibers that do not decussate at the filaments. So this is basically a movement of events basically that happen. Then we have the lateral hemispheric cerebellar pathway. Now, this is within higher animals. So it regulates initiation, planning, and timing of these volitional motor activity. So we start with the cerebellar hemisphere. So it receives input from the contralateral motor and sensory cortex via the corticopontocerebellar tracts. And remember, now this uses the middocerebellar peduncles. Then projects via the Purkinje cell axons to the dentate nucleus, right? This one also works not only with the fastigial nucleus, but also with the nucleus interpositus. And mainly it's actually the nucleus interpositus, right? Remember the emboliform and the globus, right? The dentate nucleus has got an excitatory output and then projects via the superior cerebellar peduncle to the contralateral red nucleus. So remember that, the contralateral red nucleus. Because remember, the cerebellum has got ipsilateral control. So contralateral red nucleus and the ventrolateral nucleus of the thalamus, and also the inferior olivary nucleus, right, through the tegmental tract. Then here we see the red nucleus pathway. The red nucleus projects to the inferior olivary nucleus, right, via what called the medial tegmental tract. Then here we see the inferior olivary nucleus projects via the contralateral inferior cerebellar peduncle back to the cerebellum. The circuit is done. All right, so basically that is what we see there. And this is basically the ventrolateral nucleus of the thalamus, right? This is now projecting to the primary motor area, right, nucleus, and the premotor area, area number 6, and area number 6. Then the motor and the premotor cortices, right? The primary motor and the premotor area, then lead to the fibers that descend downwards, which are the corticobulbar tracts, which basically innervate the cranial nerves. The lateral corticospinal tracts, which innervates the distal muscles, right, for voluntary movements. And here we have the corticopontocerebellar tracts that regulate the output of the neocerebellum. Now look at the clinicals associated with the cerebellum. We look at the cerebellar dysfunction. So it affects the tone of the muscles, equilibrium, and the coordination of voluntary movements. We actually see that there is hypotonia with cerebellar dysfunction. So there's a loss of resistance normally in the muscles, right? When you're actually palpating the muscles. And also results from the loss of cerebellar facilitation of the motor cortex via tonic firing of the cerebellum nuclei. So that results in what we call the pendular reflexes. So if someone does a reflex like a knee-jerk reflex, right, the leg will continue to move. That is called a pendular reflex. The other one is disequilibrium. This is now basically loss of balance, characterized by a gait, right, and trunk dystaxia. So it is an ataxic gait that you actually see there. And the patient has a tendency of falling towards the side of the lesion. So we have affected the vestibular cerebellar system. Then we have what called dyssynergia, loss of coordinated muscle activity. And we have these. Number one is dysarrhythmia. So this is basically slurred or scanning speech. The muscles of speech from the muscles of the tongue, muscles of the pharynx, and the muscles that control the larynx need a fine coordinated movement and fine coordinated contraction as well. So the cerebellum is the one that is actually told of the initial state of the muscles before the cerebral cortex commands. So if there is no coordination between these two centers, that leads on to dysarrhythmia. So the other muscles of the tongue want to contract. The muscles that are supposed to relax are contracting. So that leads to slurred and scanning speech. So that is dysarrhythmia. We have dysataxia. So dysataxia is basically lack of coordination in the execution of movements, right? Lack of coordination in the execution of movements. So basically the movement are supposed to be smooth, but here there is no coordination actually of movements. Then we have what we call dysmetria, right? So dysmetria is the inability to arrest muscular movement at the desired point. So if you're trying to reach out a certain point, right, you can shoot what we call overshooting actually. So this is whereby you fail to stop a movement at the point where you want. So that is what we call past pointing. So this is whereby a patient has to do a point to nose testing. Then we have what we call intention tremor. This is a type of dysmetria that occurs during voluntary movement. So when you want now to start a certain movement, the patient starts to have tremor. This is different from the tremor that we actually see within Parkinson's disease. In Parkinson's disease, we see a tremor that is called the resting tremor that occurs when a patient is resting. This type of tremor that we see with cerebellar dysfunction happens when a patient tries to initiate a movement. Then we've got nystagmus. So this is a form of dystaxia, basically, of the muscles of the eye, and basically happens within the horizontal plane, right? So this is what we call the ocular dysmetria. And at this point, what we actually see is that it increases when a patient is trying to look towards the side of the lesion. Then what we call dysdiadochokinesia. This is the inability of the patient to do fast, rapid movements, alternating movement actually. So you ask the patient to do pronation and supination basically of their hands. They fail to do that. That is what we call dysdiadochokinesia. Then the cerebellar lesions. So we've got what we call the vermal lesion syndrome, right? And we have what we call the anterior vermal syndromes and the posterior vermal syndromes. So basically with the anterior vermal syndrome, it results from atrophy of the rostral vermis, right? And most commonly caused by alcohol abuse. So that results in an ataxic gait that you actually see when someone is drunk, right, of the trunks and the legs. Then we have the posterior vermal syndrome. This involves the flocculonodular lobe. Usually the result is because of tumors, actually in children, brain tumors. And frequently it's caused by what we call the medulloblastomas. And then it also results in truncal dystaxia. So this little child can't sit even with their back. There is no balance actually, or even raise their head to the midline. Right? So they can't also support their head. Then we have the hemispheric syndrome. This involves one cerebellar hemisphere or two. If you affect the left cerebellar hemisphere, right, you have an ipsilateral manifestations on the body. So it can also be a lesion of the superior cerebellar peduncle or the dentate nucleus. Remember the dentate nucleus works with the lateral zones actually of the cerebellum, which is the pontocerebellar system or the neocerebellar system. So that usually results from a brain tumor or an abscess, right? And results in arm, leg, trunk, and gait, right? Dystaxia and hypotonia, right? And the cerebellar signs are ipsilateral to the side of the lesion. That is about the cerebellum.